Perfect. Hey everyone, thanks for coming, even though it's 4 p.m. on a Friday. This is Emanuele, who's a postdoc in our group at CSL and also KU Leuven through the Marie Curie Fellowship. And he's going to be telling us about some of his recent work on collapse-proof non-contrastive self-supervised learning that will be appearing at ICML.
Thanks. Thank you for coming today. It's Friday, 4 p.m. Do you prefer to have the microphone, or I can switch it off and?
Yeah.
Cool. Okay, so today I talk about collapse-proof non-contrastive self-supervised learning. This is joint work with Tim and Tina at KU Leuven, and I did this work partially there and also here at MIT through this Marie Curie Fellowship. Before delving deep into the details, let's say, let's motivate why we care about self-supervised learning. So the idea here is that we have deep learning and we can leverage large amount of data to learn some general purpose representations. And afterwards, after training these models with this large amount of data, what we can do is that in an unsupervised way, we can solve downstream tasks that do not require supervision. So for instance, we can perform depth estimation, or we can, for instance, do some semantic segmentation. And so these models somehow tend to capture the underlying semantic concepts, the underlying objects of the images when enough data is provided. So there are many different classes of self-supervised learning approaches, and here we have three. We are categorized them into three main families. So one are predictive models, which are basically based on autoencoders, where you map from an image domain to another image domain. And then you have contrastive and non-contrastive approaches. So this work actually focuses on the contrastive and non-contrastive setting, and specifically on the latter one. So before going into non-contrastive learning, let's introduce contrastive learning. In contrastive learning, what we have is that we consider a pair of images, for instance, and what we do is that we perform some data augmentation, like cropping, like flipping, rotating, or adding some noise. Then we pass these images through our network, our deep learning model. Then we project this representation on an embedding, and I will give some details later on about what these projectors are. And what we want to do in contrastive learning is that we want to enforce some sort of attraction between the embeddings of similar images. For instance, on the left, we have a beaver, and on the other hand, we have a computer. So we try to enforce some similarity across among these samples, as well as we try to repel the embeddings across different examples. And the idea here is that we would like to, at the very end, to capture a sort of similarity metric that capture the underlying semantics of the concepts in the images. But the problem is that if we consider a kind of different image, so instead of having a computer, on the right we have a bear, then the question is that, okay, before we had a comparison between a beaver and a computer, and now we are having a comparison between a beaver and a bear. And so do we repel these examples in the same manner? And obviously this is not the case, right? Because different concepts should be treated differently. And so this leads to several questions that are actually addressed in the contrastive learning setting, which are which kind of negative examples do we need? How many do we need? And how do we have to repel them? And so in this work, actually, we focus on the case where we do not have negative examples, and we just focus on the case where we have positive examples. So obviously, when you try to enforce only attraction between the embeddings, you can learn some representations that are not corresponding to what we have in input, let's say. And so we end up to have some sort of collapses. And so ideally, what we would like to have here, so for instance, um, we project these vectors onto an hypersphere, and here each point corresponds to one image. And ideally, what we would like to have is that these kind of vectors, these kind of points, are clustered together, so that each cluster corresponds to one concept. So for instance, we have the beaver here and other kind of concepts on the other clusters. So this is what we would like to have ideally. Now, what happens is that if you try to just enforce this attraction between the two branches, you can end up to map every input to the same vector. And so this is referred to the representation collapse problem. But this is not the only collapse that you can um, converge to. So for instance, you can have other families of collapses. One of them is cluster collapse, where basically two of the clusters collapse to a single one. You can have dimensional collapse, where instead of having a spread over the whole hypersphere, you collapse to a subspace of it. And then finally, you can have intra-cluster collapse, where basically some of the clusters do not have any kind of dispersion. So for the latter one, what we can think about it is that imagine you have different beavers, and all the beavers are mapped to the same vector. So you don't capture the diversity of the different concepts. So now there is a relation between all these collapses, and in particular, what we see is that the most common known collapse is actually a very specific instantiation of this different landscape of issues. And of course, when you train through this attraction, enforcing this similarity across these pair of images, you can land into one of these cases. So there are plenty of them. So we are not the first to consider the non-contrastive setting. There is broad literature in this area, let's say. And so can be categorized into two main classes. One is feature decorrelation method, and the other are clustering-based approaches. So in feature decorrelation methods, what we have is that we pass our images through these networks, let's say, and then when we obtain the embeddings here, we compute a sample covariance. And from the sample covariance, we force these covariance to be close to the identity. So in essence, what we are doing is that we are decorrelating the features of our embeddings. The other family of approaches are clustering based, where basically what you do is that is very similar to what you had before, but you introduce some clustering here, because the idea is that you would like to partition your inputs into different clusters and use these clusters as pseudo label for training your model so that you don't collapse. Now, how do these classes map into this taxonomy of different collapses? Well, if you consider feature decorrelation methods, thanks to the capability of decorrelating the features, you can leverage basically the whole hypersphere, so you don't collapse to a single subspace. Whereas clustering approaches are good at dealing with clustering, let's say. But it's not clear what these approaches do for the other kind of issues.
One question. So, do we want to avoid all this kind of practice, or some of them are actually favorable? Just curious.
Yeah, that's a good question. Actually, the idea is that if you so if I go back maybe here, yeah, the idea is that we would like to ideally arrive to something like here, because each cluster somehow contains information about the different properties of a particular concept. So you don't just want to tell, okay, I have a beaver, but you would like to explain why you have a beaver, right? You would like to identify what is the structure that define the concept, let's say. And so ideally, you would like to preserve more information than simply predicting a single concept. Does it answer your?
Yeah, but if you apply like a linear probing for density class, that don't really account that intra-cluster thing. into account. Right?
Yeah, we are going to see that in the experiments, this kind of thing. Yeah.
So typically the like dimension is going to be a hyperparameter, right?
Yep.
So is dimensional collapse really such a bad thing? I mean, we're assuming that we picked the right number there.
Yeah, that's a good question. It actually depends on the intrinsic dimensionality of the data. If you try to if you have a larger dimensional space, um, if you have a larger dimensional space and try to use as much as dimension as possible, basically you cannot use you cannot leverage the whole space because of the limitation of your data. So in reality, yeah, it's true that you have to pick the dimensionality, but that's not actually um, this is not in self-supervised learning done um, is not done theoretically. Let's say I would say is more heuristic based. But in principle, and we will see also later on that the dimensionality of these embeddings or these latent representation are pretty large, and we will see later on that actually the intrinsic dimensionality is kind of lower. We will see that we are not leveraging the whole space, and so you can kind of think that there is a sort of collapse because the representation is too large. Does it address your question?
Yeah.
Okay, I was here, yes. Okay. So the key contributions of this work are providing some sufficient conditions for avoiding the collapses phenomenon. And based on these conditions, we can provide some principles, some guidelines to devise these self-supervised learning approaches. What I will do here, I will start from the final product, let's say, from the how we are going actually to implement the self-supervised learning model, and then I will connect it to the theory. So we have these two pair of images, we pass through our backbone, and then we have our projector. Our projector actually is defined in this way. So we have a linear function where we are actually going to normalize the vectors. So we project them onto an hypersphere. See, here is the dimensionality of this vector. And then what we do is that we use an additional layer, an additional linear layer, where these matrices W are just codes, and they are orthogonal and frozen. So they are not learned throughout training. They are fixed. So they are orthogonal and fixed. Then we have a softmax where it just pushes some probability vector. So this is our projector. Yes. Sorry. So you have this matrix, let's say, where the columns are orthogonal to each other. So this is our projector, and then we provide the loss function, which consists of two terms. On the left one, what we do is that we collect all the probability vector for all the images, and then we take the average, so we can kind of marginalize over our inputs. And then what we do is that we try to match this average probability vector with respect to a prior vector. And in this case, what we consider is a uniform prior vector. The other term in the loss actually is the one that is implementing the attraction. So where basically we force the output to be invariant with respect to the data augmentation.
So if the average actually is similar to a negative sample or uniformity loss, because actually force the repetition to spread it out.
Yes, yeah. We are going to see exactly this thing now. Okay, so those are the details about the projector and the loss function. And the key ingredients of this full pipeline are the loss, the orthogonality, and the fact that these vectors are frozen, and the fact that we have normalization in the first layer of the projector. Now, let's understand why we are choosing this kind of things. So regarding the loss function, we can rewrite the loss in a simple terms where we have basically the first term is the same one as the previous. And then we can expand, let's say, the cross entropy as just a Kullback-Leibler term between P and P prime and an entropy term over P. So each of these three terms enforce three different properties. So the KL here actually is forcing P and P prime, the two vectors, to be the same. And so basically, we ideally at the minimizing this loss will force these two vectors to be equal. Then we have the entropy term, which actually forces the probability vector to be on the extreme of the probability simplex. So that means that we are kind of very confident in what we are going to predict. And finally, what we do is that we push the average prediction close to the prior. And so the average prediction will tend to be uniform if our prior is uniform, of course. So now what you can do with these three properties that you can prove basically that representation collapse and cluster collapse do not occur. And the intuition here is simple because the idea is that since on average you are going to use all the codes, so this vector actually provides you information about how the data is partitioned. And so you are going to use all of them. And moreover, you have that each vector here is very certain, right? So it means that you assign each input to one of the codes. And so basically you are going to use all the codes. And another thing that is important is that the invariance loss somehow provides some information about the semantics, okay? Because you can partition in an unorganized way, but this invariance loss enforces you to have some organization in how you partition the data. Now, we have discussed about the loss function. Now let's look at the projector and why we are focusing on these ingredients. So we have a theorem here where basically what we do is that we assume that P and P prime are the optimal solutions of the loss function that we were discussing before. So if we achieve the optimal solutions of that function loss function, then we can prove something interesting. And so also we need the orthogonality and the normalization, as we mentioned before. So the result of the theorem tells you something simple. So you can think of here to have your vector H, you have C orthogonal vectors. And of course, these C orthogonal vectors can be considered as a basis in this C-dimensional space. Now, any vector can be expressed as a linear combination of a basis. And so you can express H as a linear combination of the column of W, okay? But what this theorem tells you in addition is that the coefficients that are multiplying the different vectors are constrained. And so they are constrained in this way. So only for one input, so you get one embedding, only one code has this particular coefficient alpha j, and all the other columns, all the other codes in the matrix actually have the same coefficient. In addition to that, we have that these alpha j coefficients can have only two possible values. So the number of possible solutions here is limited. And so one interesting thing is that if you consider C very large, let's say, then what's happening is that this term gets close to a constant. And so you end up to have just a single value, okay? So, and in addition to that is that if you replace this constant value above, what you end up is that this coefficient gets 0. And so you are left out only with just a single code. Okay, so that means basically that you are aligning your embeddings to the codes. And so you can think of like having some points here on this hypersphere. And then when you increase the dimensionality, you force these kind of points to align to the different codes. Now, what we can do based on this property is that we can prove additional things. And so one other thing, additional thing that you can do is that you can quantify the sample covariance. And the way to do that is that you can pick the embeddings for all the inputs, get a matrix, and then compute a dot product between a matrix multiplication between H transpose and H. And you can show that thanks to this perfect alignment, the matrix become diagonal. And so what we are actually doing here is that we are decorrelating our embedding features without imposing that explicitly. The other property that we have is that if we consider the outer product, okay, so if we consider the multiplication of H and H transpose, what we get is that we get a matrix that is n by n, where n is the number of samples in your data, okay, your number of data points. And so you can think of this matrix as a sort of adjacency where each input is associated to one of the other outputs. So you compute a similarity, right? And so you can show that basically this matrix, thanks to the alignment property, becomes block diagonal, yes?
So your adjacency matrix here basically gives you like the L2 norm between the points, right? Because
Yeah.
it's like,
Exactly.
yeah, or I guess the squared L2 norm. Is it important that this lines up with the fact that you're normalizing things with respect to the L2 norm, or could you be normalizing with respect to any norm here in your projector?
So it's not exactly the L2 norm because it's a kind of dot product and that these vectors are not normalized. But yeah, there is a relation to that. Yeah.
These vectors are normalized, right? Because you normalize with respect to the L2 norm right before.
Right.
Right.
Yeah, it's true. Yeah, true. We will see later that they are not normalized, but yeah.
I guess my question is more like, why in the projector does it have to be the L2 norm? Like, is that an artifact of the way your proof works, or could you imagine that this could actually be any norm that you normalize?
Yeah, so the key idea is that is one of the simplest norm, let's say, and is related more to Euclidean geometry, Euclidean metric, right? So you impose the Euclidean structure, and this is quite common because you are kind of in a high dimensional, you are in a high level of your representation, let's say, where you want a simple geometry, let's say, at that level, let's say. So yeah. But yeah, in principle, you could consider different kind of geometries if you want. Yes. There is nothing to, yeah. Okay. So this adjacency matrix becomes diagonal, and each block depends on the number of components C. So if you bring this C to a large number, what you end up to have is that these blocks tend to shrink, let's say. And so in that way, you can prove that you avoid the intracluster collapse. Now, so far what we mentioned, we assumed is that we assume that our output and our size of the embeddings are the same. But in general, since we want to increase this value of C, we have to increase also the size of the embeddings H. And this can lead a problem of storing this kind of W matrix. And ideally, we cannot go beyond a certain value, let's say. So in order to deal with that, we would like ideally to increase C, but not increase F, let's say, to ensure the property that we were mentioning. But in doing so, when we consider a space of F dimensions, let's say, we can have only F possible orthogonal vectors. And so we cannot actually exploit all the C codes, let's say. we cannot have C orthogonal codes. And so what we can do here is that we can relax the notion of orthogonality, and we can go to talk about quasi-orthogonality, so orthogonality in a probabilistic sense. So how do we do that? Well, what we do is that we take our matrix and we generate this matrix using hyperdimensional computing, which means that basically what we do is that all the elements here are binary, so we can have plus and minus one. And these elements are randomly generated independently. So one of the this matrix is randomly generated and is fixed across training. Okay, so it's not learned. Now, the important property of these kind of codes is that if you take any column here and you compute the cosine similarity between two different codes, what you end up is that if you take the expectation of this cosine similarity is that if you have two different codes, the expectation is 0. And if you take the same code, let's say the cosine similarity is equal to 1, of course. So on average, these vectors are orthogonal. But if you consider the variance, let's say, of this cosine similarity, what you end up to have is that the cosine similarity is equal to 1 over the dimensionality of our embedding. And so that means that if we have a large enough space here, the variance goes to 0 quickly. And so basically, we recover the notion of orthogonality. But of course, here is relaxed. And so usually here we have hundreds, if not thousands of dimensions. And so typically this variance is very, very small. The key advantage of doing this thing is that now you can store a lot of codes thanks to this relaxation. Now, we discussed about the different collapses. We are going now to propose a methodology for evaluating these kind of issues, and we are trying to understand the performance of these models related to the question that you were asking before. So we adopted the typical strategy of training a linear classifier and measuring the accuracy on how the neural network learns this representation. But additionally, what we do is that we assess the clustering performance. We try to assess the dimensionality collapse, for instance, by taking a sample covariance and measuring if we are leveraging all the dimensions. And then what we do is that we provide a methodology to evaluate this intra-cluster collapse. And we are going to see more details about that. Now, let's start first from the linear classification. What we do here is that we use a simple ResNet architecture. We train on some simple data sets like SVHN, CIFAR10, and CIFAR100. And we compare with different methods. Here I report the main ones. In the paper, there are different baselines. So here I'm comparing with the correlating feature method. And here I'm comparing against a clustering approach. And so what you end up to have is that in terms of linear classification, we are on par with some approaches, like, for instance, Barlow twins here. And in some other cases, we do slightly better, let's say. But the performance are kind of similar. We cannot claim that we are outperforming all the state of the art, let's say. But what is interesting here is that we can learn the kind of concept, but what we want to do actually is that we want to demonstrate that we can provide retain more information about our data. And so if you evaluate the clustering performance, actually, what you end up to have, you will have a much improvement, let's say, thanks to these guarantees, let's say. So you can see here that there is a large gap between the baselines and our approach. So this is a quantitative evaluation. We can have more insights about why is that the case. And so we can go and check the different family of collapses and see why these numbers are like this.
This number seems very low.
Yeah, because we are using a very small network here.
Okay, but I mean, 5% for C410 is too low.
Yeah,
Usually there's not much gap between clustering and linear pop, like 5% or 10%.
yeah,
Very typical, but I think this is probably too much.
yeah, sure. This is a very small network. We have experiments with a larger network, and the numbers got much higher, but there is still a large gap in clustering. We have in the paper. This.
How large?
I have the numbers. If you can I go? Please remember me, and yeah, we do that.
This is like a clustering metric.
Yes.
Then where is the resonance coming from? So you're taking the output from the resonance embeddings, and then you're applying your method.
Yes. Exactly. Yeah.
What is the metric? Sorry, is this?
NMI is just the normalized mutual information, and it's just computing mutual information between your prediction and the classes of the of the of the data set, let's say.
Oh, I got it. So it's not like accuracy, like
No. It's completely unsupervised. You are not training on the labels compared to the linear classification.
You can also compute the variation of information.
Sorry?
You can also compute the variation of information if you have the ground strings.
Yeah.
Yeah, I mean, like that's another metric that is.
Okay, thanks for. Okay.
So this metric is a measure of clustering, right?
Yeah.
You try actually clustering and see what happens. Because you could literally run like k-means or something on the output of the model.
Yeah, true. No, we didn't do this experiment. Yeah. Okay, so here is some evaluation in terms of the different sizes of our output, let's say. And what we can see here is that what is interesting is that the accuracy when you actually train your linear classifier plateaus at a certain point, whereas the clustering performance still continue to improve. And so that's where we have the gain, actually. Now, I promised you to look into the different collapses. Here we focus on the dimensional collapse. So what we do is that we take our embedding, we compute the sample covariance, and then we perform singular value decomposition, and we can plot basically the different values of the singular values of this covariance matrix, and then we show it for the different approaches how these singular values are distributed. And what you can see is that Barlow twins, for instance, that is a feature the correlation method, it tries to use all possible dimensions. So here we have 128 elements in our embedding vector. And you can see that this curve is pretty flat compared to SWAP, for instance, where it drops at a very small number of values, let's say. So here you can clearly see that there is for SWAP, some dimensional collapse problem. And for our method, that is also the correlating approach, imposes some decorrelation implicitly, performs pretty on par with Barlow twins. Now, if we go and quantify the performance in terms of intra-cluster collapse, so what we do here, and probably that answers your question about the clustering. So what we do here is that we say, okay, we want to fit a mixture of Gaussian on our representation. And so what we do is that we say, okay, we fit different kind of models, so with different number of components. And for each of them, so the number of components here is 10. So for each of these 10 components, what we compute is that we compute the entropy of these mixtures. And now what we do is that we plot the entropy for each of the different components. So now what you can see is that if you look at the SWAV or Barlow twins, they achieve much lower curve compared to what we are actually achieving. And so here is the main advantage where you can clearly avoid this kind or mitigate this problem of intra-cluster collapse. Okay, one may wonder, yeah, but these were very simple data sets and a very small network, let's say, but how does it perform in more realistic cases, let's say? And so here is ImageNet-like data where we train a VIT, small. And what we did is that we perform some analysis where we compare with, again, with Barlow twins, with SWAV, with Dino, which is one of famous model in this field. And we change the number of the outputs, let's say, to see what's happening. And so here are the results in terms of linear classification. And what we did is that for each of these rows, we picked the value with the highest number, let's say. And so what you can see is that if we compare Barlow, SWAV, and our approach, we kind of get similar performance. Barlow twins actually at a certain point goes out of memory because it's computing explicitly a correlation matrix. And so it's quadratic in that case, and that's where you get this out of memory. Whereas if you see the clustering approach, actually you get good performance when you have an intermediate value of for your output, let's say. Dino actually is not that competitive in this kind of setting. So we actually use their code base, and we obtain these values, let's say these numbers, which was interesting finding. So there are lots of heuristics in Dino. Now, when we go to the clustering performance, we obtain some real gain, let's say, compared to the baselines, because we can really get some significant margin compared to the existing approaches. And yeah, that's basically it. So today we have discussed about the different families of collapses, and we have demonstrated some principles to try to avoid them. So thank you.